In this video, I'm going to show that the Mitchelson-Morley and Sagnac experiments give consistent results so that you don't need the theory of relativity to explain them. Now, until now, the Mitchelson-Morley experiment, the only possible interpretation of it is that the speed of light is constant relative to the source. The Sagnac experiment implies that the speed of light is absolute, which is the ether theory, and Einstein formulated the theory of relativity in order to account for this inconsistency. However, in this video I'm going to show that Sagnac also implies that the speed of light is constant with respect to the source, and therefore C equals CR, or the ballistic theory, is consistent without relativity. To illustrate the various speeds involved in the discussion and how what speeds one would measure in various situations, I've given these two illustrations here where I1 and I2 are inertial reference frames, and I have a source of light here which emits photons at a speed c equal to CR, and individuals A and B measuring the speed of light in these respective situations. Now, both A and B measure the speed of light emanating from S. The relativity theory says that both A and B measure C relative, whereas the ballistic theory says that A measures C relative and B measures C relative plus V. Now, for the absolute velocity, which is also the ether theory, which presumes the existence of an absolute reference frame in which C is constant, I have A and B both moving with respect to the absolute reference frame. Now, if V2 is the velocity of A with respect to B, or the velocity of I2 with respect to I1, then A measures CA minus V1 minus V2, B measures CA minus V1, and F measures CA. F is in the absolute reference frame, so he measures the absolute velocity. Now we'll go on to prove that C is equal to CR. This is a schematic of the classic Sagnac experiment showing a sequence of mirrors that reflect light in clockwise and counterclockwise directions emitted from a source and split into the two directions by a beam splitter mirror, and the two streams go around in opposite directions, come together here, and the result is observed and compared with an interference fringe that was initially established before it was rotated. And the result is that you did get a shift in the fringe. However, by this model, there should be no shift. It turns out that this is wrong. And the problem with this model is the assumption that if you sit on this experiment and a beam is emitted from the source, the assumption that it will travel on a straight line. In reality, it doesn't travel on a straight line if you're rotating with the experiment, because the beam of light travels, it has a velocity c with respect to the source. However, the beam of light does not follow a straight path in the rotating reference frame. If you rotate, the actual path that you would see if you were in the rotating reference frame is shown here and here. A better way to see that is just imagine that this is a merry-go-round. It's inside of the merry-go-round building, and the merry-go-round is rotating, and you don't know that it's rotating. Or you may know that it's rotating, but you want to throw a ball to your friend who's over here. So what you do is you aim the ball directly at your friend, and you find that instead of going to your friend, it lands behind him. And if you throw it to him if you have another friend here and you throw it to him in this direction, what you find is that since you're throwing the ball not into the direction of the rotation, the ball will land before your friend. Another way of looking at it is if somebody is on imagine an indoor target range, and you're firing at a target, and somebody, without you knowing it, lifts the whole range up, concrete and all, and puts it on a turntable, and slowly starts and slowly rotates it to a constant angular velocity, and you're unaware of this. So now you would find, if you aimed at your target, you would find that the bullet fell behind your target relative to the direction of rotation. So this observation that if you're rotating with the Sagnac experiment, the relative velocity is not straight in the rotating frame, then that's the critical point of this whole derivation and this whole demonstration. That's the physics behind what I'm trying to show, that it's the velocity of light relative to the source here is CR. However, within the actual path, it doesn't follow a straight line in the rotating frame. It follows a straight line in the inertial frame. So instead of now analyzing this, it's more convenient and more transparent to look at the ring Sagnac experiment, which is the standard Sagnac setup that's used today in all kinds of applications. And that consists of a fiber optic cable with a laser source that emits light in two directions, two opposite directions, coherent light, and that the light travels around in opposite directions, comes together over here again, and the two light streams are compared and examined for a shift. And indeed it's found that you do get a shift using this setup. And I represents an inertial reference frame, presumably for example, the surface of the Earth, and omega is the rotation of the ring of the entire setup with respect to the Earth, or an inertial frame. Now, the two different ways of analyzing this are best understood with the train analogy, and I can understand why Einstein was obsessed with the train analogy, because it's the best way to understand and see what's going on. So, for the case, assuming that C is relative to the source and that you're rotating with the whole setup, then the train analogy looks like this. In the middle of the train traveling at velocity v, you emit light at a speed c equals cr, and then obviously in this case t1 is equal to t2, because you don't know that the train is moving, so the time it takes in both directions is going to be the same. Of course, that misses the fact that in this case the light does not travel in a straight line in the rotating case. All right, now the assumption that C is equal to CA, that's equivalent to saying that light is emitted from the center of the train, but its velocity is at the light instant it's emitted, its velocity is with respect to an absolute or an inertial reference frame, so that C is equal to CA. And in that case, this photon, for example, is trying to catch up with the end, and this photon is trying to catch up with this end, which is moving toward it. So the two equations are T1C equal L plus V T1, T2C is equal to L plus V T2, from which you find that T1 minus T2 is equal to 2VL over C squared, where L is 2 pi r and V is equal to omega r. This is really a fast review of classical results. And now I'm going to analyze this situation in detail. Since with respect to the rotating frame, the light does not follow a straight path. The light only follows a straight path with respect to an inertial frame. I'm going to examine this from the viewpoint of the inertial frame and the whole ring rotating with angular velocity omega. I'm looking at a Sagnac ring. Now here I have exaggerated the situation, basically blown up what is really a differential situation where I have c is the speed with respect to the source, v is the velocity of the source with respect to, is the velocity of the source with respect to the inertial frame, and then the velocity of the emitted photons with respect to the inertial frame, in which it now moves in a straight line, is c plus v. Now the angle theta is the angle that c makes with the tangent v here, in the direction v. Alpha is the angle between c and c plus v. This is a little bit, this section here is the crux of the whole analysis, as this was the crux of the physics, the fact that this doesn't move in a straight line when you're rotating. The crux of this analysis here, it took me a while to see, is a simple geometric formula that I'll show here. So if this is a segment on a circle that makes an angle theta, shown here, where if this is the tangent here, theta is this angle theta here, then the length of this arc S is equal to 2 times r sine theta. Now, I've made the other assumptions that I've made in this is that, again, this is a blow-up of a situation that's basically an incremental differential one. And so it's, in that case, the sine theta is very small, in which case sine theta is approximately theta. And of course, alpha then is going to be very small. And cosine, I approximate cosine alpha with 1 minus alpha over 2. That's the entire setup and the whole outline of what's going on. The rest is just some careful geometry and vector calculus. Vector calculus in this case, now we have the relation that c dot c plus v is equal to c times c plus v times the cosine of alpha between them. Then multiplying that out, I get c squared plus c v cosine of theta. C dot v is cosine theta. Now it's equal to c times, and this is the other critical assumption or critical observation in the derivation, that when these are incremental tangents or close to tangents on the circumference, c and v are very close to each other. So c plus v is approximately the magnitude of c plus the magnitude of v, and that's multiplied by cosine alpha. Then if you use these approximations here, you find that alpha is v theta over c plus v. Now we have finally that s, this increment is 2r times the angle theta, which is this, and s prime, which is this segment, is equal to 2r times theta minus alpha. This alpha, a little investigation showed that this alpha is the same as the alpha between c and c plus v. And it's these little observations that came together that made this derivation possible. Right. So we have that s prime is 2r theta minus alpha, and now it was convenient to use just assuming small segments all along, but now I'm going to actually use the fact that they are differential increments so that ds is equal to 2r d theta and ds prime is equal to 2r times theta minus alpha, where I substitute for alpha, and I get this is ds prime. I didn't put all the steps of the algebra in here, so that the result of doing that is that v prime is equal to 2v times 1 minus v over c plus v. That's the final formula from this analysis. Now, in the other direction, excuse me, in the other direction, I have omega going this way, v going in the opposite direction. V go, oh no, v, in this case, let's see, v was this way, so v was in the direction of c. In this case, c is in the opposite direction to omega. So that's the situation for the going the other way around. So now I have c, I have v here, and I have the same type of picture that I have over here with just some slight differences. In this case, it turns out to be easier to just use elementary geometry, in which case the distance c minus v cosine theta, which is this distance here, minus v cosine theta, is equal to this distance c plus v times the cosine of alpha. And again, c plus, this is where the signs become very important. C plus v, shown if v is as close to a tangent, then I'll just illustrate it real quick with a, let's see, if this v actually will be something like this, that will be v, that will be c, v will be tangent this way, so it'll be in that direction up here. All right, so that will be c plus v, and this will be v. This will be v. That will be c, and this will be c. This will be c plus v, which in this configuration you can see that c plus v is approximately equal to the length of c plus v is approximately the length of c minus the length of phi. So it's c plus v is the absolute value of c plus v is c minus v cosine alpha. And again, using these approximations, and just standard algebra, you come up with the expression for alpha is this. Then again, s prime is equal to r times, in this case, s prime is, let's see, this is s, and this is s prime. In this case, s prime is longer than s, or s prime is equal to 2r. Alpha is in a different position on the other side. In this case, you have to look at the geometry. I can't go through, do that all now here. In this case, s prime is 2r times, s prime is 2r, bigger than s, 2r times theta plus alpha. Then I'm going to substitute for theta, I'm going to substitute for alpha this expression, and now label it with its correct differential expression. ds prime is equal to 2r times 1 plus v over 1 minus v d theta. And of course, take ds d theta. ds d theta is ds prime d theta. That should be ds prime d theta. ds prime. So ds prime d theta, which is ds prime d theta is v prime, which is the speed at which it goes from the origin to a point on the circle in the inertial reference frame. So v prime is equal to 2v, and v is the speed of the speed c of the light beam emitted from the source. So v prime is equal to 2v times 1 plus v divided by c minus v, if you go through the algebra. So now, finally, I'm going to look at this from the train viewpoint. Now I'll get over on the other side here. Well, I'm going to be out of view, but you're just going to have to listen to me at this point. All right. So again, I'm showing the train which basically the train represents this ring unwound. I take this and unwound it that way, this one unwind it that way. So there's the train, and here's the inertial reference frame that the ring is rotating with respect to, and now I have the speed in the inertial reference frame where the ring is rotating or moving with velocity v, and in this inertial reference frame, I have that the speed of light is c plus v double prime in this direction, c plus v prime in that direction. It's different in both directions, and that's what distinguishes this from the relative analysis. Right, now, in this case now, with the speed c plus v prime times t is equal to L plus Vt, this is traveling at a speed c plus v time v prime. It travels for total time t, during which it travels the distance L plus the distance the end moved away from it, Vt. And now we're almost home. In this case, v prime is this term here, because c plus v prime is moving in the direction of v, which is this c and v are in the same direction, and v double. So I'll substitute for, if I substitute for v prime in here and solve for t, I get t1 is equal to L over c plus v. At this point, I believe I may have dropped some higher order terms, but you have to go through the algebra to see what you can drop. Then for the other direction, I have c plus v double prime times t, the velocity of the light heading in that direction with respect to the inertial frame, times t is equal to the distance it travels, which is L minus Vt in the time t. Substituting for v double prime, which is 1 plus v over c minus v, times, you find that t2 is equal to L over c plus 3v. Finally, t1 minus t2 is equal to this expression here, 2vl over c squared times 1 plus v over c times 1 plus 3v over c, and dropping the term v over c, because v is the order of meters per second, and the speed of light is 3 times 10 to the 8th meters per second. So this is this same approximation is done when you get to this expression up here, so that you get t1 minus t2 is equal to 2vl over c squared, which is the same as the classical result found by the assumption that the speed of light is relative to its source. Frankly, I was astounded when I got this result. I did notebooks full of filled with circles and lines and geometry, and I thought that there's no way, after all. At the end, it was just stunning to come up with the classical result without using relativity. This is a very simple result. This result and the Mitchelson-Morley result say that they both agree now, and they say that the speed of light is relative to its source, constant relative to its source. Now I've tacked on one more section, which I first didn't. I intended to present it as the introduction, but then I decided to tack it on to the end. It's kind of a review of the Mitchelson-Morley experiment and some other stuff that probably may be redundant at this point, but I'm not going to go through the whole thing anymore. So thank you, and on to the next section. I'm going to briefly review the classic Mitchelson-Morley and Sagnac experiments and their results. For the Mitchelson-Morley experiment, I have a Mitchelson-Morley interferometer moving at a velocity v, assumed to be, with respect to an absolute coordinate system, assumed to be that of the Earth circulating, the speed of the Earth circulating around the sun. It consists of a source, a beam splitter mirror, reflecting mirrors perpendicular to the two paths, and the experiment consists of observing a change in the interference pattern that had initially been set up as this is rotated, as the position is changed with respect to the assumed direction of the velocity with respect to the ether. The calculation is given over here, and there's only one thing to note in arriving at the result that T34 minus T12 is this, that you have to note that 1 over 1 minus x for x very small is approximately 1 plus x. If you do that, calculate the time for these two paths, then you get that the phase shift is this term here, and the phase shift divided by lambda is 0.44, which says that for these parameters, you should expect a phase shift. You should expect a phase shift of the order of magnitude 0.44 lambda. So this is lambda. This would be shifted by a distance 0.44 lambda, which should easily be seen as a change in the interference pattern initially set up in the Mitchelson-Morley experiment. The result was that the result is a lot of experiments and variations of experiments. The result was always that there was no phase shift ever observed, from which it was included that the speed of the phonons, c, was relative to the source. From which it was included that the speed of the photons was relative to the source. Then Sagnac observed that if you rotated a Mitchelson-Morley interferometer, that you indeed experienced a shift in the interference pattern. Now, the Sagnac test of the ether theory is a representative test, or an implementation of the Sagnac test that's very common, is a ring, consisting of a photo optic cable? Fiber optic cable. Okay, I have terrible memory. Consisting of a fiber optic cable rotating at an angular velocity of omega, and rotating with it, there's a source of photons ejected in opposite directions in phase, and then observed as they come back here and examined for interference. And indeed, the result of this experiment was that there was a shift in the phase between the photons that were circulated. Now the question arose, well, what explains this experiment? Well, one explanation that's examined is that this speed c, at which the photons are ejected, is relative to the source, in which case they circulate at the same speed around the circle, regardless of the angular velocity, and so you should. This assumption, the result of this assumption is that you conclude that c is not, velocity of ejection is not with respect to the source. So then the next calculation is, if you assume that the velocity of ejection is absolute, in other words, that these go around the two circles at an absolute speed with respect to an absolute reference frame, and not with respect to the fiber optic cable, then you get that there is a shift. So that this experiment verifies that the speed of light is absolute, which directly contradicts the Mitchelson-Morley experiment. It's easier to visualize these two experiments if you think of them in a train analogy, and you think of it as in the train analogy by taking this loop and this loop and just flattening them out, so that what this one looks like in the train analogy is this is each arm. This arm, with respect to the train, we have a relative velocity c in both directions, and obviously if the source is in the train, moving with the train, or relative to the train, then the time it takes to travel to the end is going to be the same in each case. This is v doesn't matter. On the other hand, if you assume that the source is external to the train, or c is c absolute, and the train is moving at a velocity of v, then you have that the simple standard formula is T1CA is L minus VT1, T2CA is L plus VT2. And if you solve these equations, you come up with the formula phi is equal to 2LV over C, which is the classic result for the Sagnac experiment. However, where L is the circumference, of course. However, it turns out that this classic analysis is incorrect, and that indeed this does explain this result. And that is the whole point of this video. And this was the background. Thank you.